Hello students, in this lecture we're going to talk about phase changes. So now that we know about the different states of matter and what's going on at the molecular level in each state of matter, we're going to talk about how we can move from one state to another. How do we go from a solid to a liquid to a gas and back down again? So our objectives are going to be understand the relationship between kinetic molecular theory and phase changes. You should already know kinetic molecular theory from a previous lecture. And now we're going to see how we can apply that knowledge to looking at phase changes specifically. You should be able to identify whether energy is being absorbed or released during a phase change. So depending what's happening, can you tell which way energy is being transferred in the scenario? And finally, can you identify a particular phase change based on the two phases involved? And we're going to learn some vocabulary that helps us define and label particular phase changes based on what exactly is happening. So let's take some notes on phase changes. So first of all, we should probably define a phase change, and that is when matter changes from one phase to another. And you could be going from a solid to a liquid to a gas to a liquid. You can go straight from a solid to a gas or gas to a solid. Anytime we're changing from one phase of matter to another phase, we're going to call it a phase change. And this always happens through energy transfer. We have learned in a previous lecture that the transfer of thermal energy specifically is called heat. So anytime we're moving thermal energy from one place to another, there's the possibility of a phase change. So during a phase change, while it's actually happening, both phases are present at the same time. Now we saw this in class when we were melting ice, and we saw that both ice, the solid form of water, and the liquid, the what we would refer to as water, are present at the same time during the phase change. It's not like there's one instant there's ice and then the next instant there's water. There's a gradual change between the two, and during that change both phases are present at the same time. And here's an interesting thing. We saw this with the heating curve of water, that temperature actually remains constant during a phase change. This is a little bit non-intuitive. We would expect that as we keep applying heat, we're going to continuously see the temperature rise of a substance, but it's actually not true. While a substance is changing phase, so let's say from ice to liquid water, the temperature is going to remain constant at the freezing point or the melting point while that change is occurring. And this is because the energy that we're putting in is actually going into breaking the bonds of the molecules up to change it from a solid to a liquid. It's not going towards temperature. But we'll talk a little bit more about that later on when we take a look at a heating curve. Just remember for now, this point, the temperature remains constant during a phase change. Which way is energy going in a phase change? Thermal energy has to be absorbed by the substance. Absorbed means taken in, so there's energy input. Heat is going into the substance in order to break molecular bonds during a change to a more energetic phase. So a more energetic phase, or change to a more energetic phase, this could be something like a solid going to a liquid, or a liquid going to a gas. We have to put in energy in order to do that, and we call that energy absorption. That energy, what is it used for? It's used to break the molecular bonds holding a solid together, and once you break those bonds, now the substance can flow as a liquid. Or if you're going up one more level, you could put in some energy to break the bonds in a liquid, to tear apart those molecules so that they can fly around freely as in a gas. You can predict that it would go the other way for energy being released when we want to go back down the chain from a gas to a liquid, let's say, or a liquid to a solid. Then we actually release energy. Thermal energy has to move out of the object. It's getting cooler, so the temperature needs to drop. And those molecular bonds are reformed, and we move to a less energetic phase. Liquid is less energetic than gas. solid is less energetic than liquid. And we kind of know this already from our study of kinetic molecular theory, that in a cooler object, the molecules are not moving as fast. So this should kind of make sense. Let's give ourselves some terminology that will help us describe specific phase changes that we're going to see on heating curves as well as in labs and demonstrations in class. So the first one we're going to call melting. And melting is the process of changing from a solid to a liquid. And for something really easy, just think about ice. The thing that we usually think of when we hear the word melting is ice melting into liquid water. We're going from a solid, the ice, to a liquid, the water. And we call that melting. Any substance can melt. You can take a solid block of plastic and leave it out in the sun on a really hot day, and you'll notice that it becomes kind of gummy and gooey and might even start to turn into a liquid and pool around. That is also melting. So you can take any substance and melt it. The next level up, so we're kind of going up the chain right now. If we want to go from a liquid to a gas, we call that vaporization. And I want to highlight a certain part of this word called vapor. Vapor means some sort of gas. You maybe have heard of water vapor or a vaporizer that produces steam and makes the air a little bit more humid for us. That's not an accident that this root word is inside of our vocab word here. So vaporization means turning it into vapor, so turning it into a gas. This has two other words that kind of go along with it, boiling and evaporation. We may be familiar with boiling mostly from cooking, and evaporation mostly from leaving out water and it evaporates into water vapor outside, or perhaps from biology. In ecological cycles, we know that water evaporates up into the sky, condenses into clouds, and falls back down as rain. So the difference between these two terms may be a little bit subtle. They're both kinds of vaporization. Boiling means that the energy is being put into the liquid, such as water, for example, and we're boiling from within the water. When you look at boiling water, there's water turning into vapor, turning into gas inside the body of the water, and that's bubbling up. That's why we see water boiling with a lot of bubbles and roiling, and that gas then escapes upward. With evaporation, we're thinking about only the surface of the water itself, not from heat coming up from inside of the water. So this would be just like a puddle, or you leave a cup of water outside in the air, and at the top of that water, the surface of that water is going to turn into a gas and evaporate off. So a little bit of a technicality difference. You don't really need to know that too much. Just understand that both of these words, boiling and evaporation, both of them refer to the process of turning from a liquid to a gas, which we're going to call vaporization. So now let's go back down the chain. If we want to go from a gas to a liquid, now we are releasing energy. We have to go back down to a lower temperature. We're going to call that condensation. And another verb for that is to condense. Water condenses when it turns from steam into liquid, little droplets. And you may have seen this on a cold day where water is condensing onto a cold surface. If you have a very humid room, for example, and you have a very cold glass, a glass of water, a glass of soda, or whatever it is, you might see little water droplets form on the surface of the glass. And that's because the glass surface is cold, and as water vapor touches the glass surface, it loses some of its thermal energy. There's heat transfer out, and so the temperature of the water drops and it changes phase from a gas to a liquid, and we call that condensation. Finally, when we want to go down from a liquid to a solid, we call it freezing. And again, let's think about ice or water. We take liquid water and we move thermal energy out of it, heat transfer out of the water to cool it down, lower its temperature, and eventually it's going to drop below its freezing point and turn into ice, which is a solid. So now we have some words that we can use to describe specific phase changes. We can see all of these concepts in action on what's called a heating curve. And a heating curve is a graph that is going to show us the temperature in degrees Celsius on the y-axis, and either time or heat on the x-axis. So if I'm applying heat for a certain amount of time, they're going to be about the same thing. So I'm going to use the letter big Q to represent heat, and that is thermal energy that I'm adding to the system, and that's going to be measured in joules because it's energy. So if we look at what's called the ideal heating curve of water, we're going to start below 0 in solid, because when water is in a solid form we call it ice, and water freezes at 0 degrees Celsius. So this line right here is 0. That is 0 degrees Celsius. And anything below 0 degrees Celsius for water is ice. So what we have here is a solid. Then as we go up, we're adding heat, we're applying heat over here, adding thermal energy to the water, or to the ice, and eventually it's going to reach this point, 0 degrees, and start melting. And we can call this point right here, I'm going to label it point A, and point A is the melting point. I continue on up here, and I'm going up here. As soon as we've completely changed phase into a liquid, now the temperature can start rising again. Remember that during the phase change itself, the temperature is going to remain constant. So if we look at this heating curve, right here where the line is flat, this is where we're actually changing phase. And right here, during the process of melting, we have both ice and water at the same time. So two phases at the same time. And then it becomes a fully into a liquid phase, and then the temperature can start heating up again. We're going up, we're going up, we're going up, until we reach a point up here where the liquid now starts to boil. And we're going to call that process vaporization. We go up, and now the temperature is constant, just like it was during melting, because now we're changing phase. I have liquid and gas present at the same time, and you've seen this on your stove when you're boiling water for pasta or whatever. There's liquid water in the pot, but it's also boiling off steam. So both of these are present at the same time, and that is going to be at the boiling point for water, which is 100 degrees Celsius. That's about right there on the graph. After the water is completely made into steam, if we were to keep on adding heat to that steam, then the temperature can finally start rising again when it's completely a gas, and all the energy can now be used for temperature instead of breaking up these molecular bonds. So what's physically happening? How come when we add energy in here, the temperature is not rising? Well, the energy is going somewhere. It's going into the substance, and it's being used to break the bonds of a solid to turn it into a liquid. Over here, I'm still adding heat, but the temperature is not rising because all that energy is going into breaking the bonds of the liquid so it can turn into a gas. Let's look at some other points on this graph. I'm going to label this point B. I'm going to label this point C. And I'm going to label this right here point D. And where would we hit point B? Point B we would hit on the way down if we're a liquid and we're cooling the liquid down. It's eventually going to hit a point where it starts turning into a solid, and we call that freezing. So point B is called the freezing point. Notice that it's at the same temperature as the melting point. We're just going the other direction. Point C is where we start to turn the substance into a vapor. So this is called the vaporization or boiling point. And point D, we're going to hit that on the way down. So we have a gas and we're cooling it, cooling it, cooling it until it hits this point right here and it starts to condense. I'm going to call that the condensation point. Okay, so now we have some names for all these points on our ideal heating curve. Here's a task for you to practice using what we know already in the thermal energy unit. 1 and 2 should be in your notes when you come to class tomorrow, and that is to write a paragraph using our thermal energy vocabulary that explains what happens to water as it is gradually heated from a solid to a gas. Number 2, same thing, except in reverse. We're going to write a paragraph that explains what happens to water as it is gradually cooled from a gas to a solid. And if you don't remember our vocabulary words in this unit so far, we have used thermal energy, we've used molecules, temperature, thermal equilibrium, thermal contact, heat, and phase. And now we've added our new words from this lecture. We'll just call them our phase change words. And what I mean by that is our new words of melting, freezing, vaporization, and condensation. Okay, see if we can do this. Come to class prepared to discuss. Let's return to our objectives. First objective was to understand the relationship between kinetic molecular theory and phase changes. Can you relate what's happening when we change phase to what's going on with molecules in a substance? This is objective 1. If you can do that, then you're set. Can you identify whether energy is being absorbed or released during a phase change? If I said we're changing phase from liquid to gas, do you know if energy is being absorbed or released? Make sure you can do that. And finally, you should be able to identify a particular phase change based on the two phases involved. So if we're going from a solid to a liquid, you should be able to identify that as melting. If we're going from a gas to a liquid, you should be able to identify that as condensation, and so forth. Same with freezing and vaporization. If you can do all 3 of these things, then you're set.